So if we start off with a membrane, so we have a membrane, and we have a certain concentration of, let's call this the inside of the cell and outside. And there's a certain concentration, so everybody's familiar with chemistry, we write brackets for concentrations, and there's concentrations of things like potassium inside and outside the cell, and concentrations of sodium inside and outside, and chloride inside and chloride outside. Any other important ions that we know of that occur inside cells or outside cells? Calcium is an extremely important one. So calcium inside. Sorry, my handwriting is. So there's, we can calculate, depending on the concentration, the concentrations of these things are different inside and outside the cell. So the cell has these pumps which pump these ions across. So we have pumps and maintains a gradient, an ionic gradient. And that gradient, if you were just to take 2 bags of fluid, and then interface it through a membrane, so they have an infinite volume on each side, you're going to find that ions are going to start crossing across, right, down the gradient. If you open up some holes, ions are going to cross, so holes that only let sodium through are going to cross. They're going to cross from the high concentration to the low concentration, right? And what happens is you're going to start to get an accumulation of charge on the other side. And at some point, you're going to get a charge difference, which is going to have the same power as the gradient going down. And when you hit this equilibrium, this is called the Nernst potential. So let's look at the concentrations outside of a cell on is about 5 millimolar. Sodium is about 150 millimolar. Chloride is 150 millimolar. Inside, chloride is fairly low. Sodium is fairly low. And potassium is high. So we see that if we were to open up channels, potassium would not come out, sodium would go in, and chloride would go in. And we can, for each of these channels, figure out what the reversal potential for that particular ion channel is. So the reversal potential is called the Nernst potential. And the Nernst potential, we can say E for a particular ion. This is the Nernst. And that's when the chemical gradient equals the potential gradient. So it is RT over NF log of the concentration inside, or outside, sorry, divided by the concentration inside. And R is equal to the gas constant. And that's equal to 8.3 e to the 15th joules per kilomole. So, what is the K? This is temperature. Is that right? And then thanks. And then the temperature is equal to T in this is the temperature in Kelvin. And it's approximately equal to 298 at room. And F is the Faraday constant, which is equal to 9.64 e to the 24th. Is that right? Times 10. What the heck? What is this notation here? Coulombs per mole. So if we put all of these things in, oh, and N is the valence of electron, of ion. So it's 1 equals 1 for sodium and potassium, and 2 for calcium, and -1 for chloride. And so this number here is approximately equal to 26.6 millivolts at temperature equals to 310 Kelvin, which is the this is physiological temp. So we can just take the concentration outside, divide by concentration inside, take the log of that, multiply this, and it'll tell us what the potential where this gradient will happen. If you just open up a channel, that it will tell you what voltage it will sit at. And for sodium, the potential E sodium, it's positive. It depends on the concentration difference. Potassium, it's going to be positive or negative. So the same valence as sodium, but the concentration is the opposite direction. So it's going to be negative, okay? And the concentration gradient for sodium is about 10 to 1, and for potassium is about 20 to 1. So you think it's going to be larger or in amplitude than the sodium? Larger? I think it's larger. So minus 120 millivolts. And for chloride, this is minus 65, approximately. And one of the first homework you're going to pop values in and try them out. And I usually use chloride at minus 90 or something like that. So, but you'll actually take my recipe for artificial cerebral spinal fluid and the recipe I use for my intracellular fluid. So the two recipes I use for inside and outside, and you're getting the recipe, which doesn't tell you which things are important, doesn't put them necessarily in the order. So you're going to have to go figure out where are all the potassiums. Things like gluconate are big things. They don't tend to have a lot of charge, so you sort of ignore those. So there's certain things in the recipe you ignore. So you're going to have to go through the equations and sort of guess and figure out which things are important, which are not. So, any questions about that? Yeah.
26.6 millivolts, is that for potassium or is it?
No, that's the thing in front. That's universal. It's only dependent on temperature. Then for the particular ion you put in, the ion only goes in here.
Because you have N, which depends on the ions.
The valence. So if it's a minus, the valence is -1, then this becomes minus 26.6. If it's 2 for calcium, then it would be 52.5. So it would be, I really should put the N out in front, right? Well, the N can be in front. It doesn't really. It has to be 1 over N. This component here is the. So you're right. Okay. So this is assuming that these channels are open only for a particular channel, but we can combine them. What happens if we have different channels open? So this is what's called the Goldman-Hodgkin-Katz equation. So it's GHK equation. And that tells us what the reversal potential is for the entire cell. So, and that E is equal to RT over F. So this thing out here. And then we add up all the different channels. So we have what's called a permeability. Of sodium. Plus permeability of potassium plus the permeability of the chloride. Actually, we flip these guys because the chloride having the opposite sign, you can just flip it. So the question is, what's the permeability, right? And the permeability can change over time. If we open up all the channels, then it's going to give us 1 voltage. What we find is that normally at rest, permeability of sodium is much, much less than the permeability of potassium and chloride. Sodium and chloride permeability is much, much less than the potassium. So if we put in some number for the permeability that has a fairly high ratio of this to this, we'll find that the E at rest is approximately equal to minus 65 millivolts. So there's open channels. Potassium channels are a bit open. Sodium channels are mostly closed. You put it in this equation for the permeability, you get out minus 65, which is about what the voltage between the inside and the outside you would find if you poked an electrode directly into the cell. Sodium is not off. I mean, there is some sodium current, and the potassium current isn't terribly high, but the balance is closer to the potassium reversal potential than it is to the sodium reversal potential. Right? When the sodium is low, permeability, and when the potassium is low and the sodium is high, you see it move, the voltage move up. So this is what happens during an action potential. During an action potential, let's say a neuron is sitting at some resting potential. So this is minus 65, so we're going to call this rest. It's sitting, this is the voltage, we're plotting the voltage on the membrane, so I'm going to put an M for the membrane, and I'm going to plot time on the y-axis. And we're going to find, so down here is the chloride, the potassium reversal potential, EK, and somewhere up here is the E sodium Na, and let's say right here, this is 0 millivolts, right? So the cell is sitting at rest, and something comes in and perturbs. You have maybe an electrode you stick into the cell, and you inject current into the cell, and or the neuron is receiving some kind of synaptic inputs, and the synaptic inputs open up channels which depolarize the cell. And at this point, we're getting mostly just a linear change. We're injecting current, we're getting sort of a linear change in the amount of resistance. These permeabilities are not changing much. So what's changing the voltage is current coming in from other sources. Then suddenly, it hits a threshold. And so we're going to call this a threshold. And the threshold of the neuron is not, there isn't a real physical threshold. It turns out the threshold depends a little bit on how quickly you depolarize the cell and things like that. So it's sort of a philosophical idea. You get to the threshold, and what happens is the sodium and the potassium conductances both open up a lot. It turns out the sodium ones open up first and faster. So there's a little bit of time when it's just the sodium conductance permeability goes up dramatically. And what happens is that brings us up to close to the sodium potential. And then shortly afterwards, so we can plot down here, I wish I had left more space. I'm sorry, I'm going to start this graph over again. And so here's our threshold, here's our resting potential. We get up, we're going up, and this is 0, this is ENA, this is EK, this is rest. And what we're seeing here, this is the permeability of sodium, and the sodium permeability opens up. This is 1, this is 0, and this is the permeability of potassium. The sodium permeability opens up very quickly when the cell gets above the threshold. And that brings us close to the sodium reversal potential. And then it turns out the sodium conductance starts to drop off. But shortly afterwards, about the same time, this potassium conductance opens up too. And so that brings us back to, closer back to this potassium. And then the potassium drops back down and we come back to rest. So we have a sodium that goes up and down, and the potassium goes up and then comes back down. And we're seeing a couple things. What happens is these permeabilities they're voltage dependent, and in some cases the sodium is also time dependent. And we'll go through how and why that is. So this is called the action potential. And there's a phase here where we're getting a regenerative current. So it's a positive feedback loop. At the moment, if you go up, if you put in little bumps of current coming in, you'd come up, and as soon as you turn on, this is for currents of different sizes. Each pulse getting slightly larger, you turn it on, it ramps up and then comes back down. It looks kind of like a first order system, comes up and comes back down. But at some point you hit this threshold and you get this regenerative current. The current produced by the opening of channels depolarizes the cell. This is called, as we move closer to zero, this is called depolarization. And as we move more negative, this is called hyperpolarization. And these are terms I am intimately involved with all the time. I talk about depolarization, hyperpolarization. It may take a little while to get used to those. So ask me if you get confused when I'm talking about hyperpolarization and depolarization. So, yeah, and you get this little overshoot. This is called after hyperpolarization. Potential. And then it returns back to rest. So that's the action potential.